Alright, so today's class, we're focusing on optimization and inequalities in general. Usually that's more of an Olympiad topic, but it still applies a little bit to AIME. It's helpful to know a couple of basic inequalities. So let's get started. Let's start there. So I'm sure you guys all know about the trivial inequality, which essentially states that x squared is greater than or equal to 0 for all values of x, or for all real values of x. X squared is greater than or equal to 0. And that's true in general. This is known as trivial inequality, and pretty much all inequalities are derived from this inequality. So for example, we have a version of the AIME, so this is the trivial inequality. So we have a version of the AIME inequality, which states that a squared plus b squared is at least 2ab. Or, it's more commonly written that a plus b is at least 2 times square root of ab. And we can prove this using the trivial inequality, because if we rearrange, we get a minus 2 square root of ab plus b is at least 0, and we can rewrite as square root of a plus square root of b squared is at least 0. And this is true by the trivial inequality. And so because this is true, then all our steps are reversible. So we just have to check that all the steps that we did are reversible, and they are, since we only did addition and subtraction. And so because this final is true, this initial is true. Now one problem is clear, right? What happens if the trivial inequality is only true for real numbers, which means this square root of a plus square root of b must be a real number, which means that the AIME inequality, or at least this version of the AIME inequality, can only apply when square root of a and square root of b are real numbers, which means that a and b must both be non-negative. And so for trivial inequality, we have x's in the real numbers, and then for AIME inequality, we have a and b must both be non-negative numbers, not necessarily integers, but they must simply be non-negative. Otherwise, the AIME inequality does not apply. So the AIME inequality, so this here is a shortened version of the AIME inequality, but in general, the AIME inequality states that, and the reason it's called the AIME is because the arithmetic mean and the geometric mean. So it states that the arithmetic mean of n numbers, so x1 plus x2 over to xn over n, that's the arithmetic mean, is always greater than or equal to the geometric mean of these n numbers. And so we can prove this, in fact, using a special type of induction. So we first start with, with any induction, we have our base case. So for n equals to 2, it's clearly true, right? We already checked that on the previous slide. We proved this using the trivial inequality. So what about in general? So first, we proved that if this is true for n equals to k, then this is also true for n equals to 2k. So if this is true, then this is true. And so we can see that by, we know that x1 plus x2 all the way to xk over k is at least the kth root of x1, x2 all the way to xk. And then we also have x sub k plus 1 plus x sub k plus 2 all the way to x sub 2k over k is at least the geometric mean of those. And this is true because we're assuming that n equals k is true, or that this AIME is true for n equals to k. And so we have these two to start with. And so we can combine these to prove that it is now also true for n equals to 2k, because we have x1 plus x2 all the way to x sub k is at least k times kth root of x1, x2 all the way to x sub k, and then x k plus 1 plus x k plus 2 all the way to x sub 2k is at least k times the square root of these, right? Or the kth root of the product of these, all at x of 2k. So now if we add these two together, then we have x sub 1 plus x sub 2 all the way to x sub 2k, which is a significant part. And then on the right side, we have k times square root of k, the kth root of x1, x2, all the way to xk, plus the kth root of x, k plus 1, x, k plus 2, all the way to x sub 2k. And so now, remember, what we're trying to prove that is that the AIME inequality holds for n equals to 2k. And so, can we take this part and somehow turn it into what we want, which is 2k times the kth root, or the 2kth root of x1, x2, x3, all to x2k. So is this true? Well, if we apply AIME inequality on this inner expression, then we end up with 2 times the 2kth root of this product. And then we multiply by the k at the end. And so the second inequality right here holds in general. And so therefore, this inequality, this, which is greater than this, which is greater than this, and so this one must be greater than this one by transitivity of inequality. And so in general, if n equals to k is true, then n equals to 2k is also true. So now we've proven, but that's only half of it, right? We've proven that n equals to 2 works, and so this means that n equals to 4 works, which means that n equals to 8 works, which means that n equals to 16 works, but there's still a bunch of gaps in the middle. So how can we then fill in these gaps? So to fill in the remaining gap in the proof, what we proved now is that if n equals k is true, then n equals to k minus 1 is also true. So we're going kind of backwards in terms of the normal direction of induction. And so how do we prove this then? Well, we have x, in general we have x1 plus x2 all the way to xk is at most k, or divided by k, is at most k times the kth root of their product. And so to prove that this is true for k equals, or n equals to k minus 1, we simply let xk, remember this is true for any set of non-negative real numbers. And so we set xk equal to the k minus 1th root of the k minus 1th root of x1, x2, x3, all the way to x sub k minus 1. So it's the geometric mean of the other k minus 1 terms. And so now if we plug this in, we get x1 plus x2 all the way to xk is at least, now on the right side we have k, the kth root of, we have x1, x2 all the way to xk minus 1, times now xk, which we know is x1, x2 all the way to xk minus 1 to the power of 1 over k minus 1. And so this equals k times the kth root of x1, x2 all the way to xk minus 1 to the power of k over k minus 1. Right? And so this equals to k times x1, x2 all the way to x sub k minus 1 to the power of 1 over k minus 1, right? Because the kth root is just 1 over k. And so this equals to k times x sub k, right? But we're not done yet. And so, well, from here, it's pretty easy to see where we can go. We have x1 plus x2 all the way to xk is at most k xk, right? And then so we get x1 plus x2 all the way to x k minus 1 is at most k minus 1 times xk, right? And we know xk is equal to, or we substitute in the value for xk, and so we get x1 plus x2 all the way to xk minus 1 over k minus 1 is at least the k minus 1th root of x1, x2, x3, all the way to x sub k minus 1. And so if the AIME inequality holds for n equals to k, then it also holds for n equals to k minus 1. And so now we've filled in all the holes in our proof. So because it's true for n equals to 4, it's now true for n equals to 3. For 8, it's now true for 7, 6, and 5. And then for 16, it's now true for 15, 14. And you can see that it's going to hold in general for any n. And so we've officially proven the AIME inequality. But it's important to remember that this only holds when the terms are all non-negative. So if a single one of those negative, the AIME inequality no longer holds. Right? And one more thing to note is that what is the equality case? So this is greater than or equal to, but when is it equal to? Well, the equal to, it's pretty easy, right? It's simply when the equality case is simply when x1 equals x2 equals x3 equals xm. So it's simply when all of them are equal. And so that clearly gives x1 equals, x1 is greater than or equal to x1 for both sides of the AIME. And so one more thing to note is that for the trivial inequality, the equality case is x equals to 0, right? That's a trivial equality case, right? And so we've dealt with everything we need to know about the AIME inequality. So this is going to be the most fundamental inequality that we ever use, usually, in terms of AIME, at least. And there's one more inequality that we need to know, and that is the Cauchy-Schwarz inequality. Now, some of you guys might know this. Schwarz inequality. And so what this, what the inequality states is that a1 squared plus a2 squared plus a3 squared all the way to a sub n squared times b1 squared plus b2 squared all the way to bn squared is always greater than or equal to a1 b1 plus a2 b2 all the way to an bn whole squared. So in short form, essentially we can rewrite this as the sum of ai squared times the sum of bi squared is always at least the sum of ai times bi whole squared. And on these I equals 0, or I equals 1 to n, I equals 1 to n, right? So this is the general statement of the Cauchy-Schwarz inequality. Now this looks pretty complex, but first let's look at how we can prove it, and then let's look at a couple more special cases involved. So first, to prove this, we're going to make use of actually an ingenious technique. So we're going to define a function, f of x, equals to the sum of ax minus bi whole squared for I equals 1 to n. And so clearly, we have f of x is greater than or equal to 0 for all x, right? By the trivial inequality, f of x is greater than or equal to 0 for all x. And we can rewrite this. If we expand all the terms, we have the sum of ai squared for I equals 1 to n times x squared minus the sum of 2 AI bi times x plus the sum of bi squared, I equals 1 to n, I equals 1 to n. Right? So it's essentially quadratic, and so f of x equals, we'll call this a squared plus, or ax squared plus bx plus c, where a equals the sum of ai squared, b equals, so this is 2b, sum of ai times bi, and c equals the sum of bi squared. And all these are from 1 to n, so I'll just stop writing that. Alright? And so now that we know that f of x is greater than or equal to 0, for all, we know that f of x is greater than or equal to 0 for all values of x, right? And so that means that this quadratic either has a single root. So if we look at the quadratic, it looks either touches the either doesn't touch the axis, the x-axis, or does touch the x-axis. So it has either no roots, or it has a single root, right? So it has 0 or 1 roots. And so what must that mean? That must mean that the discriminant of this quadratic is at most 0, right? And so what's the discriminant of this quadratic? It's 4b squared minus 4ac, and this must be at most 0. And so we can rewrite this as 4ac must be at most b squared, or 4b squared, and so we have ac must be at most b squared. And so now if we plug in, or we substitute in the values for a, b, and c, we end up with ai squared times bi squared must be at most sum of ai times bi whole squared. Right? And so that's how we prove the Cauchy-Schwarz inequality in general. So now, one more thing we have to address about this is, what is the equality case? So this is greater than or equal to, right? So when is it equal? So equality occurs when the ratios of each of the ai to bi are equal. So a1 divided by b1 equals a2 divided by b2 equals a3 divided by b3 all the way to an over bn. So it's when the ratio of each of these is equal, right? Equal to some constant c. And that's when the equality case of this AIME-GAIME inequality occurs, right? And so some special cases where this would be useful is, for example, suppose you want to prove that x squared plus y squared plus z squared was at least 1/3 x plus y plus z squared. How would you prove this? Well, you could expand it out, right? But there's a much cleaner way of proving this. If you notice that we can rewrite this as 3 times x squared plus y squared plus z squared is greater than or equal to x plus y plus z squared. And we can rewrite 3 as 1 plus 1, or 1 squared plus 1 squared plus 1 squared times x squared plus y squared plus z squared is at most x plus y plus z squared. And so you can see that this is true by Cauchy-Schwarz, where each of the ai's are 1, right? And then the bi's are x, y, and z. And so ai times bi is just x, y, and z. And so this is it's simple to prove using Cauchy-Schwarz inequality. Alright? Okay, so we only need to know these 3 inequalities: trivial, Cauchy-Schwarz, and AIME-GAIME. The rest of it's up to algebraic manipulation. So now if we take a look at the first problem on the handout, we have let a, b, and c be real numbers such that a plus b plus c equals to 2, and a squared plus b squared plus c squared equals 12. What is the difference between the maximum and minimum possible values of c? So we want to know the minimum and maximum possible values of c, so it makes sense to isolate c by itself. So if we rewrite the two conditions as a plus b equals to 2 minus c, and a squared plus b squared equals to 12 minus c squared. Now if you notice from the previous example that we just did, we can apply Cauchy-Schwarz directly to this, directly to a and b. So we have 1 squared plus 1 squared times a squared plus b squared, but b must be at most a plus b whole squared. Correct? This is true directly from Cauchy-Schwarz. And so now we have 2 times 12 minus c squared must be at most 2 minus c squared, which gives us 24 minus 2c squared. At most c squared minus 4c plus 4. And so this gives us 3c squared minus 4c minus 20 is at most 0. Right, and we can factor this pretty easily. This comes out as 3c minus 10 times c plus 2 must be at most 0. And then so c must be greater than, to satisfy this inequality, c must be greater than 10/3 and less than -2. Or sorry, the other way around. So c must be between 10/3 and -2. And so the difference between the minimum and maximum possible value of c is equal to, so the difference between the minimum and maximum possible value is just 16/3. Alright, and so that's relatively easy to do using Cauchy-Schwarz. However, there's another way you could do this if you happen to forget Cauchy-Schwarz, or if you don't notice. So if we start off with where we started at the previous one, one thing we might notice is that we can use this to solve for AB in terms of C. Right? If we square this, we get a squared plus b squared minus 2ab, or plus 2ab, equals to 2 minus c whole squared. And so this gives us ab equals to half 2 minus c squared minus 12 minus c squared. Right? And so now we might think of somewhere we have to get an inequality, right? If we want to find a bounds for c, somewhere we have to use an inequality. So if we forget Cauchy-Schwarz, you might here use AMGM. So for example, if we use AMGM here, then we have a plus b greater than or equal to 2 square root of ab. And we can plug in the value for ab and figure that out. We could also use a squared plus b squared is greater than or equal to 2ab. We could plug in this value for AB and get us the same equation for C. And we could also use the trivial inequality with a minus b squared is at least 0. And this gives us, this, right? A squared plus b squared is at least 2ab. And so we can plug in our value for AB and our values for a plus b are a squared plus b squared and get an equation for C. Right? And so we can do this without Cauchy-Schwarz. But it's far more easier to do it using Cauchy-Schwarz. Right. And no matter which approach you use, they'll all give you the same answer because all these theorems are equivalent to each other. Or all these inequality theorems are equivalent to each other. Right. Any questions on that? Okay. So let's look at the next problem then. Let z equals to, or a set has 4 numbers, right? The 6 pairwise sums of distinct elements are 189, 320, 287, 234, x and y. Find the greatest possible value of x plus y. So this is an example of a problem where knowing all these advanced theorems doesn't really help. It's mostly just about thinking your way through. So we have, so if there's 4 distinct elements, a greater than b greater than c greater than d, then we have 6 distinct sums, right? A plus b is obviously the largest. C plus d is obviously the smallest. And then less than c plus d, we have b plus d, right? And after this, we have a plus c. And then somewhere in here, we have either either we have b plus c, or we have a plus d. And then if we have b plus c there, this one's a plus d, and this is b plus c. Alright, so we have 6 distinct sums. Right, and then we're told that these 6 sums are 189, 234, 287, and 320. And then we have x and y. So it only makes sense to, if we want to maximize x plus y, we should make these the largest. So x plus y should correspond to these two. So it should be x plus y should be the first two, right? X and y. And then these other smaller ones should be the other 4. So this is 189. This is 234. And then this should be 287. And this should be 320. Alright, so now we want to maximize x plus y. So we're looking to maximize is 2a plus b plus c, given that b plus d is 234, c plus d is 189, and then either b plus c is 320 or 287, or a plus d is, b plus c is either 320 or 287, and so is a plus d. So now how might we do this? Well, we can try to use some algebra to manipulate this, right? First thing we note is from these two that b minus c equals to 234 minus 189, which is 45. From here, one thing we can note is that a plus b plus c plus d equals 320 plus 287, right? And so that equals, let's see, 7, so it equals 607. So now that we know a plus b plus c plus d, can we figure out a plus c? A plus c should equal 607 minus b plus d, which we know is 234. And so that comes out to be, so 607 minus 234, which is 367. And then we also know that a plus b is then, right, and so a plus b is then 45 more than that, which comes out to be 4, 1, 2. And so we can add these together to get 789. And so that is our answer, right? I may have made a computation error somewhere, but you get the idea. So that's how, in fact, if we fix x and y to be the largest of these 6 sums, then there's exactly a single value for x and y, right? It's a determinate problem. And so the maximum arises from the fact that x and y could be any of these other sums as well. X and y could have been b plus d and c plus d. Right, any questions? Okay, so let's look at problem 3. Let z equals to a plus bi be the complex number with the magnitude of z equal to 5, and b greater than 0, such that the distance between this complex number and the z to the 5th is maximized. And what we're trying to find is, what is z to the 4th? So the only constraint we're given is that this equals to 5, and what we're trying to maximize is the distance between 1 plus 2i times z cubed and z to the 5th. And that, you guys should know, is equal to 1 plus 2i is the magnitude of their difference, right? So we're trying to maximize is this quantity right here. So first thing we can do, the most obvious thing to do would be to factor it out, or factor this into 2 separate things. So we have 1 plus 2i minus z squared. So this equals to, now z cubed is, this is the value of z cubed times 1 plus 2i minus z squared. And this we know comes out to be 125 times 1 plus 2i minus z squared. So now we're trying to maximize this whole thing, right? And this is a constant, so all we need to do is maximize this individual part. So now, let's look at exactly what this is. So if we look at the complex plane, so since this is absolute value, we can rewrite this as z squared minus 1 plus 2i, right? So if we have a complex number z, somewhere right here, subtracting 1 plus 2i is equivalent to moving it down, or moving it left 1 and down 2, correct? And so we end up with this new complex number, right? And so what we want to find, obviously, is which complex number having absolute value of z equals fifth allows for the greatest distance, or the greatest distance between these two complex numbers, right? So the magnitude of so the magnitude of z minus, or z squared minus 1 plus 2i is equal to the distance from the origin or the distance to the origin from this complex number, z squared minus 1 plus 2i. So if z squared starts somewhere here, and you subtract 1 plus 2i, then this magnitude is equal to this distance right here. And we know that this original distance between z and the origin is fixed at 5. So how might we be able to put z squared such that this new distance is maximized? So obviously the way it's drawn, it gets smaller, right? So if z squared is in this quadrant right here, it moves left and down, right? We get some number that's smaller than 5. If it's in this quadrant right here, it moves left, down. This number could potentially be greater than 5. If it's in this quadrant right here, it moves left and down. This distance is greater than 5, right? This is 5 right here. So this distance is automatically greater than 5. And if it starts in this quadrant and moves left and down, this distance could be greater than 5, or it might not be greater than 5. And so where's the clear location we want to put z squared? In this third quadrant, right? And so now, one thing to notice is that if we connect these 2 points right here, so this is z squared, and this is z squared minus 1 plus 2i. So this right here is 1, it has length 1, this length of 2. So what is the length of this side right here? That side is root 5, correct? So the new distance, which is what we're looking for right here, we'll call it d, forms a triangle, right? And the other two sides of the triangle are fixed at 5 and root 5 by construction. And so what does this tell us? D is at most 5 plus root 5. At most. So it could be greater, it's less than or equal to 5 plus root 5. And obviously we want to maximize D, so we want to make equal to. And so when is it equal to 5 plus root 5? When this angle is 180 degrees. And so that must mean that we want, if this angle right here is 180 degrees, that means that this angle, this angle is 90, obviously. And so the sum of these two angles must be 90. And so therefore, this triangle and this smaller triangle must be similar, right? And so what we end up with is then, and I'll redraw this, actually. So now, what we get with, if we're assuming that they're similar, or we want them to be similar, then z lies somewhere here, right? And so we know that this length is 5, this length is 1, this length is 2, this length is root 5. And so we can quickly figure out that this length is also root 5, this length is 2 root 5. And this is z squared. And so z squared equals to negative root 5 plus negative 2 root 5 I. Or which is just negative root 5 minus 2 root 5 I. And so therefore, so since z equal, or since the magnitude of z is 5, magnitude of z squared is 25, right? And so all these lengths are actually 25. So this is 25, so d is at most right? And so what's actually true is that this is 25. And so this is 5 root 5, and this is 10 root 5. And so z is equal to negative 5 root 5 minus 10 root 5, or z squared. Right? And what we're trying to find is z to the 4th. And so we can figure out z to the 4th, right? And so we can figure out the answer. Alright? So that this was the first example of a geometric optimization problem. So in the problem, it had to do with complex numbers, but in reality, it was all about geometry, right? The simplest, the solution, the inequality part of the solution came from the triangle inequality, right? We all know the triangle inequality. The third side is at most, the length of the third side is at most the sum of the other two sides, right? And so anytime you're dealing with geometric inequalities, 99% of the time it's going to have to do with the triangle inequality somewhere, right? And so if you keep in mind the triangle inequality, it helps you deal with these sort of geometric problems. So the only reason we turned it into a geometric problem is because, one, it was on the complex plane. Two, there was no other way to include Cauchy-Schwarz, AIME, GM, or any of the other inequalities that we know. And so this makes it far easier. Alright, so whenever in doubt, use geometry. Okay, so let's look at the fourth problem. Find the minimum value of 9x squared sine squared x plus 4 over x sine x. So we're trying to find the minimum value of 9x squared sine x plus 4 over x sine x for x between 0 and pi. So this looks pretty complex, right? But one thing we might notice is we're trying to minimize this, right? So I see a squared term here. So one thing that might make sense is to use the trivial inequality, right? And so if I try to change this into a square, what we have is that 9x squared sine squared x plus 6x sine x plus 4 is going to equal to 0 by trivial inequality, plus or minus. Right? Because we have 3x sine x plus or minus 2 squared is at most 0. So now if we try to use this, and I divide both sides by x sine x, then we get 9x squared sine squared x plus 4 over x sine x plus or minus 6 is at most 0. And so if we rearrange this, 9x squared sine squared x plus 4 over x sine x is at most plus or minus 6. And so what's the minimum possible value? It's obviously 6. And so our answer is 6. Alright, it doesn't even matter what x and or what x is. And in fact, we can double check that this works. So we should double check this works. So we found a lower bound, right? And we want to find a minimum value, which means we must find a solution that satisfies this lower bound. And so this equality of this inequality happens at the equality case of this inequality, which happens at the equality case of this inequality. And so the equality case of that inequality is just when 3x sine x minus 2 equals 0. And this is obviously when x sine x equals to 2/3. And so obviously there's some value of x between 0 and pi that makes that work. Right? And we can check that simply by using the fact that at 0, x sine x comes out to be, if we plot x sine x as a function, then at 0, x sine x is 0, right? And at pi halves, x sine x is pi halves, right? So if this is 0, this is pi halves, this is pi, and so at pi halves, it comes out to x sine x is equal to pi halves. And so we know that because this is a continuous function, at some point it's going to pass through 2/3, right? And so there is a solution between 0 and pi halves, in fact, not even 0 and pi, that satisfies x sine x equals to 2/3. And in fact, there's two solutions, because if you continue this, at pi, x sine x is also 0. Alright, so therefore there is a solution to this, which means there's a solution to this, which means there is a value of x that satisfies this minimum bound. And so our minimum value is therefore 6. Alright, so it's not enough to just find the lower bound. We also have to prove that there's a value that satisfies that lower bound. Okay, so let's take a look at number 5. So suppose that the absolute value of xi is less than 1 for, right? And then suppose further that absolute value of x1 plus x2 all the way to xn equals 19 plus the absolute value of x1 through xn. And we want to know what the smallest possible value of n is. So let's break this down. So our first statement is that absolute value of xi is less than 1, right? And so what we have is, or what we're told is that x1 plus x2 all the way to xn equal to 19 plus absolute value of x1 plus x2 all the way to xn. So now we know that this part is positive, right? And so, or it's non-negative, right? It could be 0. And so we have x1 plus x2 all the way to xn is at least 19, right? And so the only way this is going to be possible is if n is at least 19. And so the only way this is going to be possible is if n is at least 19, right? Or in fact, n is greater than 19, because if n equals to 19, then absolute value of x1 plus x2 all the way to x19 is less than 19. And so n must be at least 20. So now let's start there. So where can we go from here then? So first thought, obviously, is it possible if n equals 20? We know n has to be at least 20, but is it possible if n equals 20? And so we can try that. So what happens if n equals to 20? If n equals to 20, we have x1 plus x2 all the way to x20 equals to 19 plus absolute of x1 plus x2 all the way to x20. So the simplest way to do this would be to make this equal to 0 and make this equal to 19. So for this equal to 19, what would be the simplest way to do this? If we set absolute value of xi equals to 19 over 20, right? And so for this to be 0, then we must have x1 plus x2 all the way to x20 equals 0, which means we could set x1, x3, x5 equal to 19 over 20, and x2, x4, x6 all the way to x20 equal to negative 19 over 20. And so this satisfies x1 plus x2 all the way to x20 equals 0. And it also satisfies that the absolute value of each of them is 19 over 20. And so we found a solution, and therefore n equals to 20 is our minimum value. Alright, and so this problem kind of demonstrates why it's important to both confirm that the minimum value is true and not just confirm that the lower bound is indeed achievable. So our lower bound is 20, and 20 is indeed achievable, and therefore 20 is our answer. Any questions? Okay. So now, let us move on to problem 6. So for each integer, n, define s of n to be the minimum value of this sum, where a1 through an are positive real numbers whose sum is 17. There's a unique integer n, for which s of n is also an integer. Find this n. Alright. So first off, we're told that for each n, we have a sub n, or the sum of all the a sub i's, equal to 17. So this is fixed. I equals 1 to n. And what we're also told is that s of n equals the minimum value of the sum square root of 2k minus 1 squared plus an, or ai, or k squared for k equals 1 to n. Alright, so what can we do with this? Well, first off, so the variables here are a1 through an, right? Those are the things that change between n, right? So let's try s of 1. So for s of 1, in the case that n equals to 1, we have a of 1 equals to 17, and so s of 1 simply equals to square root of 1 squared plus 17 squared, right? That's a numeric value, so I'll just leave it like that. I won't compute it. Now what happens if n equals to 2? So if n equals to 2, we have a1 plus a2 equals to 17, and what we're trying to minimize is square root of 1 squared plus a1 squared plus square root of 3 squared plus a2 squared. So we're trying to minimize. So how might we do that? Well, so you can already tell that it's getting kind of tough, right? To minimize, because there's no simple formula we can apply to this. Right, there's no simple, none of the theorems that we have seem to apply to this in any ways. So there has to be a different way to approach the problem. So how might we approach it? So if we go back to how the problem is stated, if we take a closer look at this expression right here, this expression is of the form square root of x squared plus y squared, correct? Now what does that make you think? And now if this equals to m squared, then we have, or if this equals to m, then we have x squared plus y squared equals m squared. Now what does that make you think of? Pythagorean theorem, right? So somehow we have to use, or this somehow corresponds to Pythagorean theorem. So this is the length of the hypotenuse of a triangle with legs of length a sub k and length 2k minus 1. Correct? This is the hypotenuse of this triangle. And so if we make n such triangles, so if we have n triangles with the, or if we have n right triangles, with the side lengths ak and 2k minus 1, then each of the terms in the sum for s of n corresponds to the length of this hypotenuse, correct? And so what we're trying to find is the minimum possible value of the lengths of these hypotenuse. So one way we can do this is, this sum is also equivalent to what happens if we attach the right triangles according to their vertices. So this length would be a sub k minus 1. This would be 2 times k minus 1 minus 1. And we continue this. So this length would be a sub k minus 2. This length would be a sub, or 2 times k minus 2 minus 1, right? And so what is the sum in terms of this new geometry that we have defined? Well, the sum that we're trying to minimize is simply the length, or the sum of the lengths of these hypotenuses, right? And so now if we look at this on the broader scale, so there's a bunch of right triangles glued to each other, right? And they're each of varying heights and lengths, correct? So it looks something like this. And so we continue. At some point, we're going to have a point here. So first thing to notice is that each of these heights is fixed, right? The heights are just 2k minus 1. So the total height, if we look at it, is just the sum of 2k minus 1 from k equals to 0, or 1 to n, right? Now what about these lengths? So each of these lengths is variable, but what's fixed? The fixed part is the sum of each of these leg lengths, right? And what's the sum of each of these leg lengths? 17, right? And so this comes out to be 17. So now the question is, what exactly is the minimum value of S of n? So this point down here, which we'll call point A, and this point right here, point B, are fixed in proximity to each other, correct? And so the total sum of these hypotenuses, if we add up all these hypotenuses, it's like we moved from A to B, right? We walked along a certain path from A to B, and we added up the total length of that path, right? We walk along all the hypotenuses, and we add up the total length of the path. So what's going to be the shortest length of the path? It's obviously just going to be a straight line from A to B, right? If all of these triangles are similar to each other, we simply set the shortest path to be this, or the path to be the line from A to B, and that we know is the shortest path because the shortest path between 2 points is simply the line between those 2 points, and so the shortest path is simply the length AB. And so therefore, S of n equals to this length AB, and AB, we know from Pythagorean theorem, is square root of 17 squared plus the sum of 2k minus 1 from k equals 1 to n whole squared. And this sum simplifies to, so this simplifies to S of n equals to square root of 17 squared plus n to the 4th. Alright? And so now we're left with, or we've boiled, or we found an explicit formula for each of these S of n. So now we don't even need to consider the A of n's anymore. So no matter what n is, this will always be the formula for S of n. Alright? And so, or in fact, we have, right. And so, therefore, all we need to do is find the value of n that causes this to be an integer now. So if we go to this new Jamboard, so all we need to do is find the value of n that makes square root of 17 squared plus n to the 4th an integer, right? And we'll call this integer m. And so 17 squared plus n to the 4th equals m squared. And so we can rewrite this as m squared minus n to the 4th equals 17 squared. And so we have m minus n squared times m plus n squared must equal 17 squared. And so there's two ways we can factor this, or there's multiple ways we can factor this. So first thing, we can have either 1 and 17 squared, or 17 and 17. So in the first case, we get n squared equals to 17 squared plus 1, or 17 squared minus 1 over 2, which is 144. which gives n equals to 12. Or in the second case, we get n squared equals to 17 minus 17 over 2, which is 0, which gives n equals to 0. And so our answer in this case is n equals to 12. Alright, any questions on that? That was kind of a long problem. So in general, optimization, at least on the AIME level, is more about coming up with a more creative way of restating the inequality. So what we're trying to minimize was this tough algebraic quantity, but if you notice this kind of geometric part in it, dealing with Pythagorean theorem, then you realize that it's more of a geometry problem than it is of an algebra problem. So keep in mind, anytime you see this kind of square root of x squared plus y squared, or x squared plus y squared, you should always think in terms of Pythagorean theorem, or potentially trigonometry or something like that. But always think in terms of geometry when you see x squared plus y squared, or square root of x squared plus y squared, especially if it's not doable using algebra. Alright, so now let's look at problem 7. So let a and b be positive integers, satisfying ab plus 1 over a plus b is less than 3/2. What we're trying to maximize is a cubed b cubed plus 1 over a cubed plus b cubed. Wow. So what we know is that ab plus 1 over a plus b is less than 3/2. And what we're trying to maximize is a cubed b cubed plus 1 over a cubed plus b cubed. So this is, we know that it's at most some quantity. And so what we're trying to find is what is the maximum possible value. Okay. So first thing to notice is that a and b are positive integers. So if we rewrite this, we can figure out a bound for a and b, right? So if I try to solve for a in terms of b, we have ab plus 1 is at most 3/2 a plus 3/2 b, or we have 2ab plus 2 is at most 3a plus 3b, which gives us, so see I added equal sign there, should not have been there, and so we get, let's see, a is at most 3b minus 2, or a is at less than 3b minus 2 over 2b minus 3. Alright, so we've bounded a in terms of b. So now let's see what that has to do for us over here. So how might we go about doing this? So first thing to notice is that, let's try doing trial and error first. So a and b are positive integers, right? So we have that they're at most 1. So let's start with a simple value. Let's just pick a equals to 1, b equals to 1. Right? So if we plug that in here, well, first of all, does it work here? If we plug in a is equal to 1, b is equal to 1, we have 3 minus 2 over 2 minus 3 is greater than 1, which is false. And therefore, this is not possible. Now, what if we have a equals to 1, b equals to 2? Then that gives us 1 is less than, let's see, 4 over 1, which is true. And so this is a valid pair. So now if we plug this in here, what do we get? If we plug in 1 and 2, we have 1 cubed plus 2 cubed, or 1 cubed times 2 cubed plus 1 over 1 cubed plus 2 cubed. This comes out to 1. And you can see that if we swap them, the whole thing is symmetric about a and b. Right? So if we change it, this also gives us 1. Okay, so that's good so far. But nowhere we can jump into the problem, right? So now if we would try a equals to 1, b equals to 3. First, we check that it satisfies the initial condition. So we have 3b minus 2, which is 7, over 2b minus 3, which is 3, and so this is good. And so because this is true, now we plug it in, and so we get a cubed b cubed plus 1 over a cubed plus b cubed comes out to be 1 cubed 3 cubed plus 1 over 1 cubed plus 3 cubed, which also comes out to be 1. And so this would also hold if a equals to 3 and b equals to 1, correct? So one thing you might be noticing is there seems to be some sort of pattern. This thing always comes out to 1. So why is that? So what happens if we let a equals to 1 or b equals to 1? So if a equals to 1, then a cubed b cubed just boils down to a cubed or b cubed plus 1 on the top over 1 plus b cubed on the bottom, which comes out to 1. And if b equals to 1, that gives us the same result, right? So now we know that, okay, we're told that the maximum possible value is p over q, which is some sort of fraction, and so that fraction must be greater than 1, correct? So our maximum possible value, which we'll call m, is greater than 1. So if m is greater than 1, that means the values of a and b that give m must both not be equal to 1. Which means to find m, we must have a and b both greater than or equal to 2. Right? And so since a comma b must be greater than or equal to 2, now if we go back and look at the condition that they gave us, we have 3b minus 2 over 2b minus 3 is greater than a. So if this quantity is greater than or equal to 2, then we have some inequality for b. So if a is greater than or equal to 2, then we have an inequality for b. And so if we have 2 is less than 3b minus 2 over 2b minus 3. So this gives us 4b minus 6 is less than 3b minus 2, which gives us b less than 4. And so now we have a and b are greater than or equal to 2, but they're less than 4. And so that means that a and b are equal to 2 or 3. And so that narrows down our sample set quite a bit. And so there's only a couple of possibilities left to try. Right? A equals to b equals to 2, a equals to b equals to 3, and a equals to 2, b equals to 3. So in the first case, we get a cubed b cubed plus 1 is equal to 65 over 16. Second case, we get 730 over 54. Third case, we get 217 over. So we have 217 over 35. And so from here, we can choose which one is the largest, right? There's only 3 possible values, greater than 1. And so now we can figure out which one is largest. So it comes out to be, I guess, this one is largest. And this is obviously not reduced down, right? This reduces down to 31 over 5. And so this is our answer. Right. Any questions on that? Okay. So these final 2 problems are significantly more challenging than the previous 2 problems. So let's take a look at problem 8. The area of the smallest equilateral triangle with one vertex on each of the sides of a right triangle is, so what we're trying to find is what is the area of the smallest equilateral triangle with one vertex on each of the sides of the right triangle. Okay, so we have a right triangle, correct? With this being 2 root 3, this is 5, and this is root 37. So these are brutal numbers. So it reloaded my page for some reason. But these are pretty bad numbers, right? Lots of roots involved. And what we're trying to do is fit a right triangle in here. So the right triangle will fit something like this. And we want to find the equilateral triangle. We want to find the area of the smallest equilateral triangle that fits in here. So that's it. We're given no more information. So at first thought, this looks like a good candidate for coordinate geometry, because we can simply set this to be the origin. This is 0, 0. We set this to be 5, 0, and this to be 0, 2 root 3. And so this one, or this vertex of the equilateral triangle, we can call a, 0. This we'll call 0, b. Now, how do we go about figuring out that vertex? So that looks, at least just geometrically, that looks very complicated, right? But if you guys remember back to our class on complex geometry, equilateral triangles are very tough to deal with in coordinates, but they're very easy to deal with in equilateral, or in the complex plane, because of this fact that all the angles are 60 degrees, and it's easy to rotate things in the complex plane. So rather than working with the coordinate plane, let's move on to the complex plane. So all these points still hold, but now we're looking at the complex plane. So we'll call this point right here A, or this point right here we'll call capital A, so it doesn't get confusing, capital B, and capital C. And so the complex number A equals to just A, right, lowercase a, and the complex number B equals to B times I, right, since it's on the imaginary axis. Right, so now given these two, what is the location of C? Now if you remember back to complex geometry, the way we would figure this out is if we shift the whole complex plane. So first off, we're looking at, to get to C, essentially what we do is we take a rotation of A around B by 60 degrees. So we rotate point A around point B by 60 degrees. So now how would we do that? Well, first we shift everything so that point B is the origin. And so when we shift point A such that point B is the origin, we subtract B from everything. So we take A minus B. And now, to rotate about the origin, we simply multiply by cis of 60 to rotate by 60 degrees, and then we just add back B. And so C equals to A minus B times cis 60 plus B. So this comes out to be A minus BI times, now cosine 60 plus I sine 60 comes out to be half plus root 3 over 2I, plus at the end we have an extra B times I. So this comes out to be, well, this is computationally intensive, but this comes out to be A plus root 3 B over 2 plus root 3A minus B over 2I, and then at the end we have plus BI, right? And so that gives us root 3A plus B times I. And so now we have the location for C, which is this point right here, A plus root 3B over 2 plus root 3A over B over 2I. But that applies in general for every equilateral triangle, right? But what we want is an equilateral triangle that's inscribed in this right triangle, which means that this point, we want it to lie on this line, right? And so it's pretty easy to get the point to lie on that line, right? That line is defined by y equals to negative 2 root 3 over 5x plus 2 root 3, right? And so if we plug in the point for C now, and that's x and y coordinates, we have root 3a plus b over 2 must equal to negative 2 root 3 over 5 times a plus root 3b over 2 plus 2 root 3. Wow. Now using this, we can come up with an equation for a in terms of b, right? So we have, if we rearrange this, right, this gives us root 3a plus b over 2 equals to negative root 3 over 5a minus 3 over 5b plus 2 root 3. And so this gives us 7 root 3 over 10a plus 11 over 10b must equal to 2 root 3. And so what we end up with is 7 root 3a 7 root 3a plus 11b equals to 20 root 3. Wow. Okay, so now we figured out a constraint for a and b, correct? But let's go back to what we're trying to figure out, which is what is the smallest possible, what is the smallest area of the equilateral triangle? So the equilateral triangle, if we remember, the area of the equilateral triangle is equal to s squared root 3 over 4, where s is the side length. And what is the side length of this equilateral triangle? It's just a squared plus b squared, correct? Root 3 over 4. And so if we're trying to minimize this area, and so to minimize this, what we want to minimize is a squared plus b squared. So we have to keep in mind the bound a is less than 5, greater than 0, and b is less than 2 root 3, greater than 0. So we don't want to overshoot those bounds. But we're trying to minimize a squared plus b squared. So what we're trying to minimize is a squared plus b squared, given that 7 root 3a plus 11b, so we're trying to minimize this, which means it should be greater than or equal to something. Okay, given that 7 root 3a plus 11b equals to 20 root 3. Wow. So how might we do this? Well, when we're present with a squared plus b squared and a plus b, what did we do in the previous problems? We used Cauchy-Schwarz, right? So here the coefficients on a and b are no longer 1 and 1, right? Last time we assumed they were 1 and 1, but here there's 7 root 3 and 11. So now if we use Cauchy-Schwarz, so we have 7 root 3 root 3 squared plus 11 squared times a squared plus b squared must be at least 7 root 3a plus 11b whole squared, right? And so this, we know, right? This is just a constant. It comes out to 268 times a squared plus b squared. And this, we also know, is also a constant. Comes out to 1200. And so we have a squared plus b squared is at most 1200 over 268. And this simplifies down to 75. Right. So this simplifies down to 300 over 67. And so the minimum possible area, our area is at least root 3 over 4 times that, which comes out to 75 root 3 over 67. And so we simply have to prove that this works, and we can, all we have to do is solve the equations a squared plus b squared equals to 300 over 67, and 7 root 3a plus 11b equals to 20 root 3. But we can assume that based on the way the problem is stated, right, it's unlikely that this is going to be wrong. That since there's a guaranteed minimum, so it's always going to be greater than or equal to. It can never just be greater. And so we can assume that there is a solution to these two equations, and so therefore the minimum possible area is this. Alright, any questions on that one? Especially about the motivation, like how we might come up with that solution if we're actually taking the test? Oh, shouldn't the answer be 730 or 54? Is that larger? If that's larger, then yes. If that's not larger, then no. Alright. Sorry about the delay in answering your question, Michael. Okay. So, now let's deal with this monstrous final problem. So a lot of symbolism first, right? A of I is equal to, so they're defined constants. A of I equals to 1 over 2i, all the way to A of 215, and then A of 216 equals the deviation, right? It's a different constant. And then x1 through x216 are positive real numbers, such that they add up to 1. And then we're given this strange condition, right? And we're asked to find the maximum possible value of x2. Okay, so let's deal with this. So what we're given is x sub I equals to 1, right? I equals 1 to 216. And what we're also given is some strange condition, xi times xj, I is less than j, obviously within the bounds, equals to 107 over 215, plus the sum of ai over 2 times 1 minus ai x squared. Well, so our xi squared. So this is a pretty weird statement, right? So how might we fix this? First thing to notice is, how do we get this? How do we get this product, right? This equals to, if you look at x1 plus x2 plus x3, or if we just set, instead of 216, it's 3, this product equals to x1, x3, plus x, or the sum equals to x2, x3, plus x1, x2, right? And how do we usually get this? This equals to x1 plus x2 plus x3 squared minus x1 squared plus x2 squared plus x3 squared over 2, right? And so we can just extrapolate, and so this weird sum, so sum of xi, xj, I less than j, equals to half times the sum of xi whole squared minus the sum of xi single squared, right? It's not crazy to get that. And so this comes out to just 1, right? We should substitute where we can. So this is just 1. And so if we now plug this into the weird condition they gave us, this gives us half minus the sum of xi squared over 2 equals to 107 over 215. Oops. 107 over 2, right, 15. Plus the sum of ai times xi squared over 2 times 1 minus ai, right? That's pretty weird. But now if we combine these two, right, we have a xi squared term and an xi squared term. And then we move this to the other side. We get 1 over 430 equals, right, 1 over 430 equals, let's see, 1 over 430 equals sum of xi squared times, so this comes out to 1 minus ai times xi squared plus ai times xi squared over 2 times 1 minus AI, right? And so this on the top gives us simply xi squared, right? And then if we move the 2 to the other side, what we end up with is 1 over 215 equals the sum of xi squared over 1 minus AI. Okay. So now, we're given a couple of things here. We're given the sum of the xi, and we're given the sum of the xi squared, though they're multiplied by a constant. So if they're multiplied by a constant, but we're given the sum of the xi squared and xi, so we're given as something related to x1 squared plus x2 squared all the way to x216 squared. And we're also given x1 plus x2 all the way to x216, right? So by now, we've already dealt with this 4 or 5 times, so this should immediately remind you of Cauchy-Schwarz, right? And so Cauchy-Schwarz inequality tells us that if we take, so if one of the sums, we want them to be xi squared over 1 minus ai, right? And then we want the other sum on the other side should be the sum of xi, right? And so this is obviously squared. So which part are we missing? This part. And so since we want the coefficients on xi to be end of 1, we want to cancel out these coefficients right here. Correct? And so these coefficients should simply be 1 minus ai, right? That cancels them out. So now if we multiply this, so this will give us, so every term in here will be 1 minus square root of ai times the square root of xi squared over 1 minus ai. And so this cancels out to just give us xi, which is what we want. And so Cauchy-Schwarz, if we apply this, or if we apply Cauchy-Schwarz, this is what we end up with. So we have this inequality right here. So now we have a couple of numerical values that we can substitute in, right? The first one is, this is 1 over 2, and this is simply 1, correct? Now, this sum is a sum of constants, right? So we can sum this in such a way that, or we can calculate the sum, right? ai is equal to 1 over 2 to the power of I, except for a216, which is equal to 1 over 2015. And so this comes out to be, let's see, 216 minus the sum of ai. And the sum of ai is equal to, let's see, it's half plus 1/4 plus 1/8, all the way down to 1 over 2 to the power of 215 plus 1 over 2 to the power of 215. And you can tell pretty easily that this comes out to be 1. And so this comes out to be 215. And so we have 215 times 1 over 215 is greater than or equal to 1. Or we have 1 greater than or equal to 1. So this is in fact the equality case of Cauchy-Schwarz, because both sides are equal to each other. And so now we can apply the equality case, right? We know the equality case is true. And so in the equality case, if you remember, the equality case states that xi squared over 1 minus ai over 1 minus ai is equal to a constant for all possible values of I, right? And so this comes out to be xi squared over 1 minus ai squared is equal to a constant. And so xi over 1 minus ai is equal to a constant. And so xi is equal to a constant times 1 minus ai, right? And so we found a formula for xi in terms of 1 minus ai, or in terms of ai. Now, there's one thing we have to be careful about, is that the only free variable left is what this constant is, correct? So this constant could be anything. But we have to keep in mind that the sum of xi is equal to 1. And so the sum of xi is equal to the sum of constant times 1 minus ai. And so this comes out to be the constant times the sum of 1 minus AI. And we already calculated the sum is 215. So we have 215 times the constant equals 1. And so our constant equals 1 over 215. So in fact, there is no free variable. These variables are fixed. So x2 comes out to be 1 over 215 times 1 minus 1/4. And so this is 3 over 860. And that's it. There is no maximization or minimization. There's only a single possible value of x2, which is 3 over 860. Right? So the maximization part of the problem was only to hint at, they could have just as well asked this problem they could have just as well asked you to find the value of x2, not the maximum possible value of x2. And if they did, that would be a much harder problem because you would not know to think in terms of equality. But if they ask you for the maximum possible value, that's how we figured out that, okay, maybe we should think of Cauchy-Schwarz inequality. And so that gave us the equality case, which then gave us a singular value for x2. All right, any questions for this last problem? Okay, so that is all I have for today. And so this is our last class, at least for the summer session. And we won't have a fall session, but we're thinking about, we might have future sessions and some other special events that we will inform you about. But I've enjoyed teaching you guys for the past 4 weeks. Right, and I will post all these resources online or on the Google Classroom right after class. And I believe you have one more class, Daniel's class, later in the week. But other than that, I will see you guys later. Bye.